Hello everyone, welcome to our project final presentation for STAT 512. We are group 13 and the 5 members of our team are Chancellor Clark, Gabriel Fear, Suyash Jadhav, Hongyue Wu, and Mingmin Liu. I will start the introduction part and hand over to my teammates to discuss further. The data we acquired for our project was originally used to build an artificial neural network model in Professor Aicheng Ye's paper. He was trying to model the compressive strength and optimize the material selection for concrete. From literature review, we found there are lots of similar studies to model concrete strength based on time and materials. However, the study results may vary because of different testing environment and different testing methods. Most of the studies show that water has a negative impact on compressive strength, and cement as the fundamental material often has significant impact on compressive strength too. The objective of our study is to reassess the dataset and build a linear regression model using RStudio to understand the relationship between different variables with concrete strength. The goals for our projects are listed here and will be further discussed in the conclusion. We also want to mention the limitations of the dataset. For example, the fly ash is sometimes not reported and assumed to be zero. Superplasticiers were from different manufacturers of different chemical compositions, so there are unobserved heterogeneity in some of these variables. Furthermore, using this as the age variable may be misleading or getting a non-significant correlation result, since the difference in concrete deteriorate may be seen after years. The data was obtained from the following link, and by clicking the link, it will lead you directly to UCI machine learning repository. The name of this dataset is Concrete Compressive Strength. Follow the instructions below. You will be able to find the data folder and download it. It is noted on the website that reuse of this database is unlimited with retention of copyright notice for Professor Aicheng Ye.
Much for my partner's presentation. I'm Hongyue Wu. I will be responsible for part 2 and part 3. Part 2 is about the dataset characteristic. Our sample size is 1030. We have 8 predictors and 1 response variable. They are all continuous. Then part 3 is about the preliminary analysis. First, we use box plot to show the outliers of our predictors. There are 6 predictors who have outliers here. Then from the histograms, we can see the distributions of our predictors. There are 4 predictors who show the normal distributions, while the other 4 predictors show non-normal distributions. Then we try to understand the correlations between the different predictors. First, we get the scatter plots to show their relationships. It shows that there are linear relationships between different predictors, such as superplasticier and water and coarse aggregate, and water and fine aggregate. However, due to our large sample size, this plot may be not clear enough to show the correlation. So we also got the correlation matrix to show the covariances between different predictors. It shows that there is multicollinearity among variables, and it probably be due to the variable water here. Then, when we try to do the preliminary analysis of our model, we use all the 8 predictors to build the full model. According to the results, the cement, blast furnace slag, fly ash, water, superplasticier, and age have significant impacts on concrete compressed strength because all of their p-values are smaller than 0.05. However, the coarse aggregate and fine aggregate don't show significant impacts according to the p-values. And our adjusted R-square is 0.6125 and the standard error is 10.4. We also got the residual plots of our full model. It shows that there are clear nonlinear predictors, especially the age, and it may impact our model, so we need to focus on this point during our next step. Also, we try to do the Shapiro and BF tests to show whether there's violations of the assumptions. And the results show that both the BF test and Shapiro test are smaller, the p-values are smaller than 0.5. It means that they are both violations of the two assumptions, which are constant variances and normal distribution. Then we need to do something to deal with these violations, so we try to transform y using Box-Cox method. The best lambda is 0.7 here, and we use this transformed y to build the new model. Then we use the two tests for the new model. However, the two sets still show the violations of both assumptions because the p-values are still less than 0.05. So it means that there are some problems of our full model. So next, we will do some model selection then.
After preliminary analysis, the next step was model building. So in this slide, we do a very basic assumption check, that is to see if predictor variables contribute to the response variable, and we find that there are at least some predictor variables whose linear impact is not equal to 0. In this slide, we build a full model, and the summary is given from this image. We see that the RMSE found for the full model with all the predictors is 10.4, and the adjusted R square is 61.25%. After finding out the full model, it is important to check which variables add extra value to the response variable. Hence, added value plots are studied in here in this slide. So these plots are used for the full model and are seen in the right hand side image. So we observe that less value is added by superplasticizer, the coarse aggregate, as well as fine aggregate, and hence more analysis with the help of ANOVA type 2 can be done to eliminate these variables from our full model to obtain a reduced model. In this slide, a type 2 ANOVA test is done on the full model, where we find that the coarse aggregate and fine aggregate have p-values which are greater than 0.05, and hence only after checking for multi-collinearity between those two predictors we will be able to eliminate the fine aggregate and coarse aggregate from our full model to form a reduced order model. So in this slide we check the multi-collinearity between the explanatory variables, where we see that the VIF for coarse aggregate and fine aggregate is close to 1. Similarly, as highlighted in the slide 8, we also observe the other multicollinearities, that is the multicollinearity between water and superplasticizer, the one with water and coarse aggregate, and the multicollinearity between water and fine aggregate. But for all the three uh, explanatory variables, we see that the value is close to 1. Hence, there exists no multicollinearity between our explanatory variables. So we eliminated the two predictor variables, which are the coarse aggregate and fine aggregate, in our reduced model, and we find that the RMSE of our reduced model is 10.41, and the adjusted R square is 61.18%. For a full model, we had observed that the adjusted R square is 61.25%, and the difference between the adjusted R square between the full and the reduced model is 0.7%. So although there is a decrease in R square which is very negligible, we can use this model for further diagnostics. In this slide, the best subset model is used. So as the value of CP, SBC, P and PRESS-P is lower for model 6, which is a reduced model, and the value of adjusted R-square is higher and AICP is lower for our full model. So based on that, we run the 5-fold cross-validation test on both the models, that is model 6 and model 8. We observe a slight difference in RMSE and adjusted R-square as seen from the pointer. So hence it's always better to choose a reduced order model, that is model 6, as it induces less variance in the overall response variable than the full model.
We began our diagnostic analysis looking at outliers and influential points. We identified 57 X outliers according to the HAP matrix leverage values, 2 Y outliers according to the studentized residuals, but no points were found to have major influence according to Cook's distance. Continuing our diagnostic analysis, we found that the reduced model displayed both a lack of normality according to the Shapiro-Wilk test and heteroscedasticity as demonstrated by the Brown-Forsyth test. Looking now at the residual plots, we can see that the predictors cement, blast furnace slag, water, and fly ash appear to have relatively equal variance, while significant heteroscedasticity is observed in the age predictor, and that's also reflected in the fitted values. After trying several other X transformations, we found that taking the natural log of the age predictor solved the problems of heteroscedasticity and lack of normality in the residuals. This transformation also significantly increased our multiple R squared to 0.8161. We next tried weighted least squares, which failed to improve our model. Transforming Y according to the Box-Cox procedure also failed to improve our model. Since taking the natural log of the age predictor was our most successful transformation, we decided to plug this predictor back into the full model. The two-way ANOVA result suggests that superplasticizer can be dropped from the newly transformed model. Consistent with the two-way ANOVA results, the added variable plots also suggest that superplasticizer can be dropped from the new model. Using all predictors except the superplasticizer predictor, and transforming the age predictor by taking the natural log is validated here by best sub selection. Our final model of concrete strength as a function of cement, blast furnace slag, fly ash, water, coarse aggregate, fine aggregate, and the natural log of the age is validated here with 5K fold validation. This model displays an increased R squared value and a reduced RMSE. A final diagnostic check on the new model shows that the age predictor and the fitted values display much less heteroscedasticity than they did before the transformation and the new model selection.
The next few slides contain a general summary and evaluation of our model and results. It is important to note that the dataset analyzed was created specifically to evaluate the effectiveness of artificial neural networks at predicting concrete strength. Our initial assessment of our explanatory and response variables showed that there were issues with distribution, collinearity, and non-constant variance. The final model we selected included all variables and involved a natural log transformation of the age variable, fixing the issues of non-normal distribution and non-constant variance. Over 80% of the variation in concrete strength was accounted for by our model. The correlation between our chosen predictor variables and our response variable is strong, though a decent portion of the variation is still unexplained. A direct comparison between our conclusions and those in the literature must also be done carefully, as the literature does not report raw statistical data as we have done here. For example, different variables were chosen to be omitted during statistical analysis in the various references we looked at. The methods of analyzing the data using artificial neural networks or traditional linear regression techniques were both effective in identifying the most significant factor influencing the total compressive strength, namely cement and water content. The figures at the left are from Yi Cheng Ye, Modeling of Strength of High-Performance Concrete Using Artificial Neural Networks. They compare predicted versus actual concrete strength. As you can see, they both demonstrate that there is a decently high reliability of both methods, but the bottom figure shows that predictions made by neural networks more closely resemble actual values. Thus, it should be concluded that linear regression models are not the most suitable means by which to estimate the total compressive strength of concrete.